This isn't science fiction. This is the story of 3I Atlas, the interstellar comet that broke every rule we had, revealed the beautiful, chaotic truth of the cosmos. On the 1st of July, 2025, the world was sleeping, but the machines were awake. In the thin, cold air of the Rio Hurtado Valley in Chile, a robotic eye swiveled silently, drinking in the starlight. This was Atlas, the asteroid terrestrial impact last alert system, our planet's tireless night watchman. Its job is simple, but vital. Scan the entire visible sky every 24 hours, hunting for the near-Earth objects that might, one day, mean us harm. It's a job of immense patience, sifting through the predictable clockwork of the cosmos for anything that moves differently. And on that night, something did. A pixel shifted. A flicker of light bent where it shouldn't have. It wasn't the lazy looping drift of an asteroid, a familiar neighbor on a predictable path, nor was it the graceful curving arc of a comet bound by the gravitational chains of our sun. This was a straight line, a cosmic bullet. When the system flagged it, the numbers that came back were scarcely believable. 137,000 miles per hour. 420 million miles away from us, already tucked inside the orbit of Jupiter, but screaming in from the black void beyond our solar system. This was only the third time in human history we had ever caught a visitor from interstellar space. The third messenger, and this one was different. You've probably heard about the first two. Back in 2017, there was Oumuamua, the infamous cigar-shaped enigma. It was strange, tumbling end over end, and it was gone before we could get a good look, leaving behind a wake of tantalizing questions and a handful of wild theories. Then, in 2019, came 2I Borisov. It was far more familiar, a classic comet with an icy tail, behaving just as we'd expect a comet from our own neighborhood to behave. It was reassuring, almost boringly normal. But this new object, officially designated 3I Atlas, the 3I for Third Interstellar Object, Atlas for the survey that found it. This one shattered our sense of normal. Different speed, different chemistry, a different path. And here's the detail that made astronomers around the world physically lean forward in their chairs, the detail that turned a routine observation into a race against time. Its destination. On October 29, 2025, when 3I Atlas was predicted to reach perihelion, its closest point to our sun, it wasn't going to dive in for a fiery embrace. Most comets do. They plunge deep into the inner solar system, their icy bodies erupting in spectacular fashion as they're blasted by solar radiation. But 3I Atlas was projected to keep its distance. It would swing by at a cool 1.44 astronomical units out, about 130 million miles away, just skimming the inside of Mars's orbit. It would never even cross Earth's path. Why? Why travel across untold light-years of empty space, only to stay so far away from the campfire at the center of our system? What does that strange distance tell us about where this object has been, and more importantly, what it's made of? What secrets was it trying to keep? The universe had just thrown us a curveball, except this one was traveling in an impossibly straight line. The data that underpins this incredible story isn't from press releases or sensational headlines. This is the real stuff, the hard science. We're talking about observation logs from NASA published in the summer and fall of 2025. We're talking about peer-reviewed data from the James Webb Space Telescope's near-infrared spectrograph, findings from the Very Large Telescope in Chile, and meticulous orbital calculations from the Minor Planet Center. This is the work of research teams at UCLA, the Pontifical Catholic University of Chile, and the SETI Institute, the people on the front lines of cosmic discovery. They weren't just looking at a comet. They were decoding a message. Let's rewind to the moment of discovery. The Atlas telescope in Chile got the first hit, flagging object A11PL3Z. It was faint, a ghost on the digital sensor. Immediately, the global astronomical community kicked into high gear. Follow-up observations poured in from the Zwicky Transient Facility at Palomar Observatory in California. Teams began digging through archival images, a process called pre-discovery, and they found it. The comet had been lurking in our skies since June 14, 2025, but it was too dim, too unassuming to have triggered the automated alerts. It had snuck in. Then came the orbital calculations, and the numbers were staggering. A velocity of 61 kilometers per second, an eccentricity of 6,141. Now, what does that number even mean? In orbital mechanics, an eccentricity of 0 is a perfect circle. An eccentricity between 0 and 1 is an ellipse, like Earth's orbit. An eccentricity of exactly 1 is a parabola, an escape trajectory where an object makes one pass and never returns. Anything above 1 is a hyperbola, an open-ended path, a flyby. And 6,141? That is the most hyperbolic, the straightest trajectory ever measured for an interstellar object. It was more than 5 times Oumuamua's 1.2 and nearly double Borisov's 3.4. This thing wasn't just visiting, it was punching a hole straight through our solar system, barely acknowledging the sun's gravity as it passed. It was a cosmic rebel. On July 2nd, the SETI Institute, an organization dedicated to the search for extraterrestrial intelligence, hosted a live broadcast. This wasn't a UFO announcement, but it was the next best thing. A panel of scientific heavyweights, Dr. Simon Steele, Dr. James Davenport, Dr. Ariel Graykowski, and Dr. Wael Farah, confirmed the unbelievable truth. It was definitively interstellar. The race was on. Every major telescope on and off the planet swiveled to stare at this new enigma. Hubble, Webb, the new Spherex Observatory, the Very Large Telescope, Gemini South, the Vera Rubin Observatory. Everyone wanted a piece of 3-Eye Atlas before it swung behind the sun in October and disappeared from view. On July 21st, the Hubble Space Telescope gave us our first family portrait. At a distance of 207 million miles, it captured an image of a ghostly, teardrop-shaped coma, the cocoon of gas and dust boiling off the hidden nucleus. To get the shot, Hubble had to lock onto the comet and track its motion, causing the background stars to streak into long lines. It was like taking a picture of a speeding car from another moving vehicle. The coma itself was huge. Pre-discovery images from the Vera Rubin Observatory showed it had swelled from about 8,100 miles in diameter on June 21st to over 11,600 miles by July 2nd. This thing was active. The nucleus, the solid body at the heart of the storm, was hidden inside the glow, but estimates placed it somewhere between half a mile and 3.5 miles in diameter. Most likely it was under a mile across. Small, but it was already punching far above its weight. Then, on August 6th, the James Webb Space Telescope, our most powerful eye on the universe, turned its near-infrared spectrograph on the visitor. A spectrograph is an amazing tool. It doesn't just take a picture. It breaks down the light from an object into its chemical fingerprints. It's how we can tell what distant stars and galaxies are made of without ever leaving home. And the fingerprints Webb found on 3-Eye Atlas were bizarre. Carbon dioxide. It was everywhere. Not just a little, but a shocking amount. The mixing ratio of carbon dioxide to water was 8:1. Think about that. Why? What could make a comet so fundamentally different? The scientific community quickly coalesced around 2 main theories. The first is a story of incredible loneliness and endurance. Radiation exposure. Imagine this comet, drifting for billions of years in the vast empty space between the stars. It's not truly empty, though. It's filled with high-energy cosmic rays, protons and atomic nuclei accelerated to near the speed of light by distant supernovas and black holes. These particles are like microscopic bullets, and they bombard anything floating in the interstellar medium. Over eons, this relentless cosmic radiation would have profoundly altered the comet's surface chemistry. It would break down chemical bonds, strip away molecules, and effectively cook the outer layers. A study led by Matthew Hopkins, published in July 2025, calculated from the comet's velocity that it could be between 7 and 14 billion years old. That means it could have been wandering the galaxy for longer than our Earth has even existed. During that unimaginable expanse of time, water ice, which sublimates, turns from solid to gas, more readily under radiation than CO2 ice, could have been slowly boiled away, leaving behind a concentrated crust rich in carbon dioxide. The comet's weird chemistry could be a scar, a testament to its unimaginably long and lonely journey. The second theory speaks not to its journey, but to its birth. Formation location. Every young star is surrounded by a swirling disk of gas and dust called a protoplanetary disk. It's within this disk that planets and comets are born. And these disks have frost lines, or Jungfrau snow lines. Just like on a mountain, where it gets colder as you go up, it gets colder in a protoplanetary disk as you move away from the central star. Different chemicals freeze at different temperatures, and therefore at different distances. Water freezes at a relatively warm temperature, around 2 to 3 astronomical units out. But carbon dioxide needs it to be much colder, below 120 degrees Celsius, so its frost line is much farther out, around 10 to 20 astronomical units. If 3I Atlas formed in the frigid outer reaches of its home system, beyond the CO2 frost line, it would have naturally been born with a much higher proportion of carbon dioxide ice. It would be a chemical native of a deep freeze environment. Most comets in our solar system that formed way out past Neptune are rich in other volatiles, like carbon monoxide or methane. The CO2 dominance of 3I Atlas suggested it came from a part of a solar system we have no direct analog for. It was a far-orbit comet from another star, kicked out into the galaxy before it ever got a chance to be cooked by its own sun. Have you ever thought about your own origins? Not just your family tree, but your atomic origins? The very elements in your body were forged in the hearts of stars that lived and died billions of years ago. In a way, we are all interstellar travelers, carrying the chemical history of the cosmos within us. What story does your chemistry tell? The strange clues kept piling up. On August 20th, the Very Large Telescope in Chile detected another chemical fingerprint in the coma. Atomic nickel vapor. Nickel isn't unheard of in comets. We've seen it before, even in the interstellar comet 2I Borisov. But here's the twist that made everyone scratch their heads. There was no iron. In our solar system, nickel and iron are cosmic buddies. They typically appear together in comets because they originate from the same minerals in the nucleus, usually in a ratio close to 1:1. But 3I Atlas was spewing out 4.6 grams of nickel per second, with zero detectable iron. It was like finding a single glove without its mate. What could this mean? One explanation is that the unique surface chemistry, altered by those billions of years of radiation, had somehow trapped the iron in less volatile minerals while allowing the nickel to escape. Another, more radical idea was that the parent minerals in the Comet AS nucleus simply never had much iron to begin with. Dr. Thomas Puzia, an astronomer at the Pontifical Catholic University of Chile, put it perfectly in an interview with Smithsonian Magazine. We just cracked open the door to a whole new world of chemistry that we never had access to before. Then came the cyanide. On August 14th, the same telescope detected hydrogen cyanide gas, a common molecule in comets. It's often one of the first things to appear as a comet heats up. As 3I Atlas got closer to the Sun, the cyanide production ramped up dramatically, tripling in just 1 week in mid-September. On its own, this wasn't unusual. But when you add it to the carbon dioxide dominance and the nickel without iron, the complete chemical profile of 3I Atlas looked like nothing we had ever seen. It was a chemical Frankenstein, stitched together from pieces that shouldn't fit. In early September, the Gemini South Telescope, also in Chile, captured a stunning deep-field image. The coma looked puffy and had a distinct reddish color. This reddish hue is a telltale sign of complex organic compounds called tholins. Tholins are formed when simple ices like methane or nitrogen are irradiated by ultraviolet light or cosmic rays. They are what give Pluto its ruddy tint and coat many of the objects in the Kuiper belt at the edge of our solar system. Seeing them on 3I Atlas was another confirmation of its ancient, irradiated past. It was wearing the sunburn of a billion-year journey. Then, on September 2nd, the comet proved its toughness. It flew directly through a solar storm, a coronal mass ejection from our Sun. A massive cloud of magnetized plasma slammed into the comet's coma. For comparison, when a similar storm hit Comet Encke back in 2007, its tail was completely severed. But 3I Atlas, no reported damage, no tail break-off. It just shrugged off the impact and kept going. This resilience hinted at a surprisingly dense, compact nucleus, or perhaps a coma composition that was less susceptible to magnetic disruption than our familiar water-rich comets. This visitor was a survivor. As it continued its journey, its path took it close to Mars. On October 2nd, it passed within 18 million miles of the red planet. This was a unique opportunity. A fleet of spacecraft orbiting Mars, ESA's Mars Express and ExoMars Trace Gas Orbiter, and NASA's Mars Reconnaissance Orbiter, turned their instruments away from the Martian surface and toward this distant visitor. It was a long shot. These instruments are designed to photograph a planet from only a few hundred miles away, not a dim comet 18 million miles distant. But there was a chance they could capture something. The data downloads would be slow, with the full results not expected until February 2026. The suspense was building. By early October, the comet was a cosmic freight train. It was traveling at 152,000 miles per hour, its trajectory so straight, it was practically a line. Its origin pointed back toward the constellation Sagittarius, toward the very heart of our Milky Way galaxy. But its velocity told a more nuanced story. It was moving away from the galactic center and upward, out of the main galactic plane. This high vertical velocity is a characteristic of stars in the thick disk of our galaxy, a halo of older stars born 7 to 14 billion years ago, when the universe was younger and had fewer heavy elements. 3I Atlas was likely a relic from one of these ancient systems. A team led by Jair Pérez Couto used data from the Gaia Space Observatory, which has mapped billions of stars, to trace the comet's path backward for 10 million years. They found dozens of encounters with other stars, but none were close enough to be its parent. The trail went cold. It had been wandering for far too long. Then came the main event, perihelion. On October 29, 2025, at 11:44 UTC, 3I Atlas reached its closest point to the Sun. As predicted, it stayed far out, at 136 astronomical units. This distance is key. Solar radiation drops off with the square of the distance. At 136 AU, the comet was only receiving about half the solar energy it would at Earth's orbit. This was enough to vigorously sublimate its volatile carbon dioxide ice, but not enough to release much of its water, perfectly explaining the 8:1 CO2 to water ratio. The comet was simply too far away to get hot enough to turn on its water faucets. This also told us something profound about its past. If this comet had ever made close passes around its own parent star, its outer layers would have been stripped away, exposing a rocky core or a water-dominated interior. Instead, we were seeing a comet still coated in its original, volatile-rich outer layer. It was a pristine object. It had likely formed in the cold outer regions of its home system, and was ejected into interstellar space before it ever got the chance to be properly cooked. It was a perfectly preserved time capsule from another world. Shortly after perihelion, the comet entered solar conjunction. From our perspective on Earth, it passed directly behind the Sun. For 5 long weeks, from October into November, it was completely lost in the Sun's glare. Our most powerful telescopes were blinded. For 40 days and 40 nights, humanity lost sight of its mysterious guest. It was a calculated blackout period, a time of waiting, wondering what the Sun's heat was doing to this strange visitor. But we had an ace up our sleeve. 162 million miles away, on its own long journey to Jupiter, was the European Space Agency's JUICE spacecraft. It had a front-row seat. As the first telemetry packets began to trickle back to the control center in Darmstadt, Germany, the science teams, running on caffeine and adrenaline, finally saw what happened when 3I Atlas met the Sun. It didn't just pass perihelion. It detonated. On October 29th, precisely as predicted, the surface of the nucleus reached a critical temperature. The pressure of water ice, trapped and sublimating beneath the insulating crust of carbon dioxide and tholins, had been building like a geological time bomb. And at perihelion, that bomb went off. The JUICE spacecraft's ultraviolet spectrograph saw it happen in real time. There was a sudden cataclysmic spike in hydroxyl radicals, the telltale signature of water vapor being violently ripped apart by solar radiation. In just 90 minutes, the water outgassing rate exploded. It went from a paltry 6.6 kilograms per second to an astonishing 4,500 kilograms per second. That's a nearly 700-fold increase. The once dominant carbon dioxide output also surged, but only by a factor of 10. The famous 8:1 ratio of CO2 to water had violently inverted. For a brief, brilliant moment, 3I Atlas had become a water-rich comet after all. Dr. Anna Klein, the lead scientist for the UVS instrument, presented the findings at an emergency ESA press conference. Her face, projected on screens worldwide, was a mask of exhausted elation. "We were witnessing a process of exfoliation," she explained. "The comet's outer layer, the crust that had been bombarded by cosmic rays for billions of years, was blown off. A section of the nucleus, estimated to be at least 2 square kilometers, had violently ruptured." JUICE's high-resolution camera, Janus, captured the stunning aftermath. The faint teardrop coma transformed into a brilliant fan-shaped spray of dust and ice, erupting from the nucleus at over 100 miles per hour. The fresh material caught the sunlight, and the comet's brightness jumped from a predicted magnitude 14 to an observed 7.2. It became nearly 50 times brighter, briefly visible to well-equipped amateur astronomers on Earth as it crept out from behind the Sun. But the most shocking image was this. The nucleus was no longer a single point of light. It was a cluster. The object that had entered our solar system was now at least 3. The nucleus had fractured. A primary fragment, 3I Atlas A, remained the largest, but 2 smaller pieces, B and C, were seen drifting away, each trailing its own tiny coma. This dramatic breakup definitively ruled out the idea of a large, solid nucleus. This comet wasn't a rock. It was a rubble pile, a loosely consolidated agglomerate of ice and dust, barely held together by its own feeble gravity. It was a cosmic snowball that had finally cracked under pressure. Think about that moment of transformation. The comet traveled for billions of years, cloaked in a dark, mysterious crust. It presented one face to the universe, but under the pressure of its closest encounter, its true nature was revealed. The heat and stress didn't destroy it. They liberated the pristine, ancient water trapped within its heart. How many of us go through life with a protective outer crust, shaped by our long, lonely journeys? What does it take for that crust to break, to reveal the authentic, brilliant truth we hold inside? What pressures in your life have revealed a part of you that you never knew existed? On December 19, 2025, the caravan of fragments made its closest approach to Earth. At a safe distance of 167 million miles, they were a disappointment for stargazers, too dim to be seen with the naked eye. But for our great observatories, this was the moment of truth. The James Webb Space Telescope fixed its golden eye on the debris field. The same instrument that had first revealed the CO2-rich nature now tasted the fresh material excavated from the comet's core. And the spectrum was a revelation. The water was there, in abundance, but it was chemically old. The ratio of deuterium, a heavy isotope of hydrogen, to normal hydrogen was one of the highest ever measured, 3 times that of Earth's oceans. This D2H ratio is a fossil fingerprint. It's a clue to where and when water ice originally formed. High ratios are characteristic of water that condensed in the extremely cold, diffuse environments of interstellar space, long before a star even ignites. 3I Atlas wasn't just from another star system. It was made of primordial material that predated its own parent star. It was a frozen piece of the very interstellar cloud from which its home system was born. The mystery of the nickel without iron also found its resolution. The Very Large Telescope detected faint signatures of a volatile compound called iron carbonyl in the expanding cloud. Over eons, the iron on the comet's surface had been locked into less volatile minerals by cosmic rays, while the nickel remained in a more easily vaporized form. But deep inside, in the protected interior, the iron existed as this volatile iron carbonyl. When the outburst exposed this virgin material to sunlight for the first time in billions of years, the iron carbonyl instantly vaporized, releasing iron atoms into the coma. We hadn't been seeing a lack of iron. We had been seeing a comet with layers. As Dr. Puzia explained, we were seeing a comet with an irradiated iron-poor skin and a volatile, iron-rich heart. We just needed the sun to peel it open for us. By February 2026, the data from the Mars orbiters finally arrived. The images from the HiRISE camera on the Mars Reconnaissance Orbiter, taken just 27 days before perihelion, provided the final crucial piece of the puzzle. Advanced computer models revealed the nucleus's original shape. It was a contact binary, 2 smaller bodies that had gently fused together, looking like a cosmic rubber duck about 2.6 miles long. The model clearly showed deep fractures along the neck, connecting the 2 lobes. This was the weak point. The outgassing and rotational stress had targeted this pre-existing fault line, tearing the comet apart. The seeds of its own destruction had been carried with it across the galaxy. The fragments continued their journey, sweeping past Jupiter in March 2026. The gas giant's immense gravity gave them one final gentle nudge, allowing for an unprecedentedly precise calculation of their trajectory. They were leaving, and they were never coming back. The Vera Rubin Observatory, now in its 2nd year of operation, will track the fading fragments as they recede into the darkness. It will find the next interstellar visitors, 4I, 5I, and 6I. But 3I Atlas will always be remembered as the one that put on a show. It didn't just fly by. It performed. It shed its disguise, revealed its ancient heart, and broke itself apart for science. By July 2027, a scientific consensus had formed, published in a landmark review in Nature Astronomy. The story of 3I Atlas was complete. It was born in the cold outer disk of a star in the Milky Way's thick disk, perhaps 9 billion years ago. It was a contact binary, formed from primordial deuterium-rich interstellar ice. It was ejected by a giant planet in its home system and wandered the void for eons, its surface cooked by cosmic rays into a reddish, CO2-rich crust. Its trajectory brought it here by pure chance. The modest heating it received was just enough to trigger a catastrophic structural failure, an outburst that was the first and last act of its solar-induced life. The debate about artificial origins, briefly stoked by its strange behavior, was settled. As astrophysicist Avi Loeb conceded, Its self-destruction was a powerful Occam's razor. It behaved exactly as a loosely bound irradiated rubble pile should. The alien wasn't its origin, but its chemistry. As the fragments of 3I Atlas coast silently toward the Oort cloud, too faint now to ever be seen again, they leave behind a transformed field of study. Interstellar objects are no longer just curiosities. They are messengers. They are free samples of planetary building blocks from across the galaxy, delivered right to our doorstep. We learned that other solar systems can be wildly different from our own. We learned that these objects can carry ice that predates their own stars. And we learned they can be fragile, breaking apart to reveal their secrets. The story of 3I Atlas is more than just a fascinating astronomical event. It's a mirror. Its journey across billions of years and unimaginable distances, only to transform and break apart in the light of a new star, holds a profound lesson for us. We are all, in our own way, interstellar travelers. We journey through the years, collecting experiences, developing a protective crust shaped by our environment. We present a certain version of ourselves to the world. But life, like the sun, has a way of applying pressure. It brings challenges and encounters that heat us up, that test our structural integrity. And sometimes, under that pressure, we fracture, we break. An outburst happens. It can feel like the end, like a catastrophic failure. But as 3I Atlas showed us, a breakdown can also be a breakthrough. The rupture revealed its true, pristine core. It was only in breaking that its deepest secrets were shared with the universe. Perhaps our own moments of breaking aren't just moments of pain, but moments of revelation, where our own authentic primordial core is finally exposed to the light. It's in those moments that we, and the world, get to see what we're really made of. The comet was a rubble pile, a loose collection of pieces held together by a weak force. It reminds us that strength doesn't always come from being a solid, unbreakable rock. There is strength in resilience, in the ability to hold disparate pieces together on a long journey, and there is grace in knowing when to let those pieces go. The next interstellar messenger is already out there, hurtling through the dark. And this time, thanks to the violent, revealing, and beautiful spectacle of 3I Atlas, we'll be ready. We'll know what to look for. We'll be waiting to see what new rules it breaks, and what new truths it has to teach us about the cosmos and about ourselves. Thank you for joining me on this incredible journey. I hope this story has sparked your curiosity as much as it has mine. Take care of yourselves, stay curious, and keep looking up. I wish you and your loved ones nothing but good health and clear skies. And if you value explorations like this, the best way to support our work is to subscribe to the channel. It lets us continue bringing you these stories from the frontiers of human knowledge.